Now let's do an example of a KB problem. We've got butylamine, which we know is a weak base, and we want to find the KB. Again, I don't really know the formula, so I'm just going to do a generic equation. B standing for my weak base. If you stick that in water, that can form bases we know accept protons. So if this proton leaves H2O, that's going to form HB plus, and I'm left with OH minus, both of which are aqueous. From this, I can write my KB expression to be concentration of HB plus times concentration of OH minus all over the concentration of B. Well, initially the B was 0.230 molar, and you don't have any ions when you first stick it in water. What I'm more concerned with is, where are we at equilibrium? Well, at equilibrium, the hydroxide was 8.6 times 10 to the negative 6 molar. And every time a water loses an H plus, not only does it form a hydroxide, it also forms an HB plus. It's a 1-to-1 ratio, which means I'm going to have the exact same concentration of HB plus as I have OH minus. These came from the B. Every time a B gained one hydrogen, it formed HB plus. So if I started with 0.23 molar of the B, and some of it turned into HB, namely 8.6 times 10 to the minus 6 turned into HB, that means I don't have as much B anymore. So when you subtract that from the 0.23, we can find out our B concentration at equilibrium. So let's just plug in our numbers. HB was 8.6 times 10 to the negative 6. The hydroxide is also 8.6 times 10 to the negative 6 because it's 1-to-1 ratio. The B originally was 0.23, but I have to subtract 8.6 times 10 to the minus 6. And when I do all of that, I can get a KB value to be 3.2 times 10 to the negative 10. No units on a KB, it just gives relative strength.